we're going. So, relative speed. Or what happens when there's more than one moving object. Let's say you're driving down the freeway with your speedometer reading 100 kilometers per hour, and a Ferrari hurtles by you with its speedometer reading 180. Tow truck's parked at rest on the side of the freeway. What's the tow truck see?
Oh, this is like the red.
No, it's not the red and blue light. No, it's a tow truck's parked on the side of the freeway. You fly by, your speedometer reading 100 kilometers per hour. The Ferrari flies by, its speedometer reads 180. What does the tow truck driver see?
The tow truck sees you going 100 and the Ferrari.
Yeah, so it sees you going 100 kilometers per hour, and it sees the Ferrari VF, not final, but Ferrari, also going 180 kilometers per hour. What do you see? Yeah, you see the Ferrari going 80 relative to you. And what do you see the tow truck driver doing? Going negative 100. Because you may as well be standing still, practically. Tow truck driver is just going the other way real fast. And Ferrari passes you at 80. What's the Ferrari see? You going backwards at negative 80. And the Ferrari sees the tow truck driver as, whoops, negative 180 kilometers per hour. Now, I took this from a guy named Mr. Dewick. So let's talk about this. We've talked, this portion we've talked about already. This was the train questions we did right near the beginning. How does it, if you are passing a train, you guys are going in the same direction, what do you do with the velocities to find the relative velocity between you two? If you're traveling in the same direction, you subtract. If you're going 100 and someone is passing you at 110, they kind of are crawling by you. You know in your head, because you're both, like the context says, we're both on the freeway, we can see the the trees flying past us. You know they're probably going 110, you're going 100. But practically speaking, it would look exactly the same as if you were just sitting on the side of the road, eating a popsicle on a lovely summer day, and a car rolled by you at 10. Okay? Practically speaking, as far as what you observe, I mean, there's all sorts of unintended consequences, i.e. if you were to stop both of you, it would be awful compared to the 10 kilometer an hour. But from what you see, passage of the car, they are equivalent. Which is why it's so staggering to pass on the freeway by something that much faster than you. There's an intuitive piece. Like I remember I was on the way to a flight I had to catch really early in the morning, and we got passed on the freeway by a motorcycle like we weren't moving. It felt to me like I wasn't moving, sitting on the side of the freeway, and a motorcycle ripped past our car. And then you make the adjustment. No, we're traveling at 100, which means he was probably going at least 200 kilometers per hour. It was insane. And then if you're moving towards each other, what do you do with the relative velocities? You add them. So the relative velocity of any moving object depends on your point of view, what we are going to call a frame of reference. If you see them coming towards you, that relative velocity is going to add, because you give them all of your velocity plus the velocity they themselves had. Otherwise, they're going away from you, you're not moving, and you're subtracting their velocity from yours. So you've likely experienced this before. I'm hoping you've experienced something like this before. The classic example is the moving walkways on a moving sidewalk somewhere. You've experienced this on an escalator, perhaps as well. You have the stairs beside the escalator, and you're going up the escalator, and you can be walking. But if you walk at the same speed that the escalator is coming down at you, and you're walking, you can be walking at the same speed as the escalator and not moving at all relative to the rest of the world. Unless you're moving. Yeah, have you ever tried this? Okay.
Just sprint.
Yeah, this is, something we do as children. Or you walk on a moving walkway in an airport, either one way or the other. Walking at normal speed, walking with the walkway, you're flying. Even though, as far as you're concerned, as if you're looking at the walkway, you're just walking normal. But if you look at the bookstores that are flying by you, you're walking much, much quicker. The frame of reference you use alters your experience of what's happening. Walking the wrong way on one of those walkways is the same. You're hoofing it, or you feel like you're hoofing it. And you're like, yeah, I'm going. And then you look at the bookstores and you're not moving. Again, it all depends on how you, your frame of reference, how you experience the world around you. So you've got someone walking on a train. The train also happens to be moving forward. This is like walking with the walkway. Person standing on the ground beside the train is going to see this guy moving how fast? 16.2. So we say this is the relative velocity is 16.2 meters per second for our dude walking on the train car. The relative velocity in this case is going to be what? Yeah, the relative velocity as far as this guy passing this guy is going to be 13.8 meters per second. He's not passing the guy standing beside the train quite as quick. There's a video that I'm going to toss in here for you guys. There's a whole bunch of YouTube clips. I don't know if you've seen this one before. Okay, so what you're about to see is this. If you shoot a ball out of a cannon, what should happen? It will shoot out. What if the cannon is moving the same speed as you're shooting the ball, but going in the other direction? What do you mean? The cannon is moving in one direction. It's going to shoot a ball the other direction, and the cannon is moving at the same speed the soccer ball is when the soccer ball gets launched. Sorry? You say the ball should stay in the cannon.
The cannon's moving backwards. It's going faster with the ball. It's going opposite the ball's movement.
It's going opposite the ball's movement.
Oh, so then I need to just not.
You should not move. You just want to see it. Okay. Here we go. So here it is. So what they've got is she's driving the truck. Corey's on the back. They've got an air compressor cannon with a soccer ball in the barrel, and they're going to bring it up to speed. They've already done the calculation. It's easy to calculate the muzzle velocity of a ball. You just shoot it, see how far it goes. You can do all those calculations. Labs you were supposed to do last year.
They're going to get it. The pressure's on Grant for a perfect.
Oh, sorry, that's Grant, not Corey.
That looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
So. It's just an air. It just falls. Look at that. Hey, I mean, look, it doesn't move at all. It's going straight in.
What would have happened if they would have just let go of the ball while they were traveling forward? No, like, so the temptation is to see this and say, okay, the truck was moving forward. They just dropped the ball. What would have happened to the ball had they just dropped it? It would have continued on. Now it's a ball in projectile motion that has a component of velocity in the x direction. And if you just drop it, it would have followed truck and just dropped to the earth. What they've shown here is, well, this relative velocity stuff that I'm trying to argue here. They've got a ball, the truck's traveling at the same speed that the ball would have been launched from the cannon. They shoot the cannon, ball drops straight down. So quite a neat effect.
For 3 days of suffering, that single shot brings the myth to an end.
Can't be happier. We actually got the speed of the car to match the speed of the soccer ball. And we got the perfect breakdown drop.
Basically, the loss of physics are still hard work.
That's always encouraging. Okay. So, we've done a bunch of these examples. I don't need to do more of these, do I? You remember how these things work? We're like, you're cool with the problems, the catching up problems and that kind of stuff? Okay. Then let's skip ahead to the real cool stuff. Here's a question for you. An application of this stuff. You had two guys, Nick and Cole. They're having an argument at an airport on a windy day. Nick says that airplanes should take off with the wind. The wind pushes them from behind so the plane travels faster on the runway. Or Cole says that airplanes should take off into the wind. He's not sure why, but it makes sense to him. Who is correct? Do you take off into the wind or you take off with the wind?
Well, if you go into the wind, you're gonna get wet. Yeah.
I mean, that's really what it comes down to. Right? It's the understanding of how a plane works. If the plane got into the air because its wheels were spinning really fast, you would want to do what? You'd want to go with the wind. But that's not how planes take off. How do planes take off? So the speed of the plane is which kind of velocity do you care about when you're trying to take your plane off? Relative to the ground or relative to the air? Relative to the air, because it's the air traveling over those the wings rather, that are going to get you up off the ground.
Oh, so what if you drove a plane into a bird?
So, for example, you've got a plane sitting stationary on the ground. It is just bouncing. It's coming. Okay, and that's a full-size plane. Got lift. Theoretically, if the propeller was moving on the front of that thing, it could now go wherever it needs to go. You have a Cessna that just underwent vertical takeoff, which is terrifying. So in that video, the speed of the plane relative to the ground was what? 0. The speed of the plane relative to the wind was enough to get that plane, hello Yashvi, enough to get that plane taking up off the ground. Whatever the takeoff velocity for that Cessna is. Okay, skip ahead. We've done all this before. It's the trains. We should recap it. Okay, fine, flip back. Let's do one example. How long does it take these two trains to completely pass each other? This is way back. Online video from, when did we start this quarter? February? I've got two trains, a 150 meter long trains traveling at 13 meters per second and a 100 meter long train traveling at 5 meters per second. How long does it take this train to pass this train? What do you do? Okay, so this situation is the same as what equivalent situation using relative velocities? Sorry? Sorry, no, I mean like give me exact numbers with this. So the relative velocity here is 8 and the relative velocity here is 0. So it's like this train, the 100 meter train is not moving, and the 150 meter long train is moving at 8 meters per second. So then this becomes a much simpler question. How long does it take these two trains to completely pass each other? The question becomes, no, it doesn't really matter anymore about this train here. What you're asked to find now is how long it takes the back of this train to travel how far. The 150 is going to get it from the back to where the front was. And you have to travel another this distance. So the total distance that the back of that train is traveling is what? 250. This becomes T equals D over V. I want to travel 250 meters, and I'm traveling 8 meters per second. That's 31.25 seconds. Really easy when you just shift it, just like we did with our voltages on those plates. It didn't matter what the individual voltages were, it just mattered what the difference was. It doesn't matter what the individual speeds are here, or the velocities here. What matters is the relative velocity, or the subtraction or addition of those velocities. Is that enough review? Okay. So if that's enough review, let's skip way ahead. We'll just jump down to here. The short version to calculate the relative speed if they're traveling in the same direction. Subtract them. If they're traveling in opposite directions, either towards or away from each other, you add them. And there's more videos there, but I don't think I need to convince you. So I think we're just going to keep going. Would you like to watch relative velocity motorcycle near accident? Okay, let's find relative velocity motorcycle near accident. Where did it go? Okay, I can't show you that one because it's not there anymore. Okay, flip the page. Here we go. Skip ahead to here. I don't think it's in there. This used to be, this is what I would give, because special relativity used to be part of the Physics 11 curriculum. We'd go through this a lot slower, but we've seen this all kind of already. You guys are good with this kind of stuff. So, relativity and time. Imagine we had a cannon that would launch a baseball at exactly 30 meters per second every time. Why is there what, sorry? It's supposed to be flame on a wick. Supposed to be a flame on the wick. Watch how it soars. So imagine Sam, our bat catcher here, is the target. He's holding a baseball glove. He's standing still. What does Sam see? Yeah, he sees the ball traveling at 30 meters per second. Now situation 2 is the exact same. Ken is on the roof of a van. Van's driving towards Sam at 15 meters per second and shoots the ball. What does Sam see? The ball's coming towards him at, is it 14 or 45? The ball is traveling. So the ball already has a velocity of 15 meters per second when it's shot from the cannon at 30. So the ball now has what velocity? 45.
I know, I'm just confused what the other option is.
What they're confusing this with the soccer ball video I just showed you. Okay? No, but the cannon is moving in the same direction as the ball is being shot. It's like if I stand still and throw something versus, like a pitcher would do, versus, for those of you who watch baseball, versus what a fielder would do, catch the ball, like start running or hopping towards and then let go. Like you're imparting a little bit additional forward velocity onto the ball when you're trying to bomb it out from the field versus a pitcher who's doing this from a standing position. What happens if the van with the cannon on top is moving the other direction? This is equivalent to the video I showed you. What does Sam see if the 30 meter per second cannon is traveling away at 15 meters per second? He sees the ball coming at him at 15 meters per second. Now, let's go larger. Let's find a larger cannon that moves to and from us. That cannon is the sun. What it is shooting towards us is light. This is the basis for the Michelson-Morley experiment, which is the basis for some really weird stuff. You want to talk about it before I show you video, or do you want the video first?
A handful of experiments.
Does anyone recognize that voice?
No.
Okay. Wow, Ashton. Yes, it is, actually. Here we go. So, in the late 19th century, so read that as the 1800s. That was the 19th century. A. Michelson and E.W. Morley conducted an experiment. They thought they could measure the difference in the speed of light hitting the Earth in two situations. We've got the Earth traveling around the sun. It's basically a circular orbit. Not quite, but basically. So as far as the Earth receiving light from the sun, because the sun is in the middle and the Earth's constantly traveling around it, it's not traveling nearer to or away from the sun. You can't necessarily use our sun. But what you could do is you could look at distant stars. As the sun, or as the Earth travels in this direction, from January to July, you should see one speed for the light reaching the Earth from different stars. And then as you start to round this bend, in July, well, actually, this would be January to whenever spring is, March. You're traveling towards that light, and then March to September, with a maximum speed in July, you're traveling away. And then, September, you start to move back towards this distant light coming in from these distant stars. What they expected was, and what would be similar to what you would expect from this cannon problem. You're running towards, or the cannon is running towards you. When it shoots you, or shoots at you, that ball is going to be moving faster. When you're running away, or the cannon is running away from you and it shoots back at you, the ball is moving slower. Because that's what they expected to see with light. They expected two slightly different answers, which would make sense, right? Like we understand now, looking at relative velocities, this would make sense. Okay? In January, the Earth was moving toward the star with speed u relative to the sun, and the speed of the light relative to the sun was assumed to be some c value for the speed of light. The measured speed relative to the Earth was predicted to be c plus u. This would make sense because they're coming towards each other. In July, Earth is moving away from the distant star, and the predicted measurement of the speed of light was c minus u. Again, predicted being the key word there. The expected results did not materialize. Instead, they calculated the same speed of light for both situations. This was like situation 2 and 3, given the same value. It doesn't matter if the cannon is moving towards you or away from you, the ball is still coming at you at 30 meters per second, which doesn't make sense from a classical physics point of view. So there is now an inescapable conclusion, and people railed against this experiment for years. Einstein hated this experiment for a long time. The inescapable conclusion is this: that light is somehow special, and that the speed of light is constant for all observers. It doesn't matter if you're the one catching the light, or the one shooting the light, or the one watching the light being shot from the side. Doesn't matter what's going on, light is moving at some constant speed, c, for all observers. Which makes no sense, Joseph, you're correct, based on the classical physics that we understand, and that was laid down by Newton. The Michelson-Morley experiment is one of the most famous negative results in physics. They went out to test something and it failed spectacularly. It showed that experimentally that the speed of light in space is the same for all observers regardless of their velocity or the velocity of the source of the light. The speed, flip the page, of light simply does not depend on your frame of reference. No evidence could be found that space could be used as a fixed frame of reference.
Arc velocity compared to speed of light so little that it would be.
No, 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 because the speed of the that would imply that the implication there is that this should scale up. That objects in space should behave similarly. But objects in space are moving very, very quickly. There would be, however small, a measurable effect. If, for what Joseph just said, oh, we're just moving so slow. Well, you on this planet are moving slow. If you're running down the hallway with a flashlight, yes, your speed is minuscule compared to the speed of the flashlight as you turn the flashlight on. But things traveling in orbits or galaxies separating themselves aren't traveling at minuscule speeds. They're traveling at colossal speeds as these things travel but make their way across the universe. And even at those speeds with those objects, it was not found to be any different, which is weird. They see each other traveling at sea. Yep. That's like what happens if I accelerate a flashlight to the speed of light and I turn it on.
Oh, it won't turn on.
But it will. And the light leaving the flashlight will be leaving at the speed of light, even though the flashlight itself is also traveling at the speed of light. It's weird. So the short version of this is special relativity. And it's whether it makes sense to you or not, this is experimentally verified. We know the universe behaves a particular way. We don't necessarily understand why. We just know that it does, and there are implications for it. So the short version of this, the speed of light is a constant. Okay? The speed of light is a constant. And that constant, c, we round it, it's like 2.9 something. We to make, for simplicity's sake, we round it as 3 times 10 to the 8 meters per second. So that's what, 300 million meters per second? Couple meters, yeah, so it's moving. So the implication here, if speed equals distance over time, or, let's expand this to cosmic levels. Speed is space over time. Then how can we have the same speed for light? The next implication is this. Space and time, therefore, must change depending on the situation, which we're not used to. We would say things change, other things change, time doesn't change, and the space, the universe itself doesn't change. But with light remaining constant, the only way for that to be true is if some space and time, we were wrong about space and time, that they change and that light remains the constant. Was that a hand I saw there? Yes. 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 There's something here also called the twin paradox, which we can talk about too. Okay, so I'm going to show you a brief video. Neil deGrasse Tyson explaining the Michelson-Morley experiment. Here we go.
Only a handful of experiments in physics that completely transform physics. And many people's top of the list would have to be the Michelson-Morley experiment. In the 19th century, physicists thought that since sound waves travel through air, light waves must travel through some sort of medium as well. They called this theoretical medium ether. The famous luminiferous ether, this magical medium that was hypothesized to be what light required to move through the vacuum of space, just the way sound requires air to move from one place to another. How else could waves of light move through the vacuum of space unless there was some medium there, some hypothetical medium? Let's call it the ether. Ether, they theorize, is an invisible nothingness that permeates the universe. Its only physical property is that it allows light to propagate through it. But once precise measurements of the speed of light became possible, testing the predicted effects of ether on the speed of light became possible as well. The Earth orbits the Sun at about 66,500 miles per hour. If light travels through ether, they reason, then as the Earth moves through the ether, the speed of light should be different going with the ether than perpendicular to it. In an attempt to show the effects of ether on the speed of light, Albert Michelson and Edward Morley conducted an experiment in 1887 at what is now Case Western Reserve University.
Michelson was an expert in optical experiments. He thought that he could devise an experiment where one would be able to see the slight difference in the speed of light measured on the Earth if you measure it along the direction of the motion of the Earth and at right angles to it. There should be a slight difference.
Compared to the speed of light, Earth is not moving that fast. So if you're going to check the difference in the speed of light measured with the movement of the Earth compared with transverse to it, you need a level of precision that no one had before. The Michelson interferometer is just such an apparatus.
Michelson and Morley devised an apparatus that would detect minute differences in speed between two beams of light. Light from one source is split into two directions through a half-silvered mirror. These beams are bounced between other mirrors and then recombined back into a single beam. When two light beams combine, if their waves are completely synchronized, the peaks combine to make an even more intense peak. If they are one half wavelength off, their peaks combine and cancel out the intensity. Slight differences in speed between two light waves will therefore produce a pattern based on the amount of interference between the two beams. This is known as an interference pattern.
Questions so far? We've seen this in Physics 11, yes? Waves? Did Morrison do waves with you guys? Not with Grosser Hill this year. Hands up if you saw waves with Morrison when you did Physics 11. Okay, some of you. Are those of you who didn't see it, are we cool with what's happening here? Questions? Okay.
Examining the interference pattern from the two light beams sent out in different directions would clearly show that the speed of each light beam were different in different directions.
Sort of pause again. Fun fact. This is the same way, you guys know what LIGO is? The Gravitational Wave Observatory. You guys have heard of gravitational waves? Okay. This is like the most groundbreaking thing that happened in physics in like the last 10 years. So the gravitational waves have been theorized as things that exist. When massive objects, when black holes merge with each other, they theorized that waves of gravity, which is a weird concept to think about, would ripple space. And so they set up something very similar to the apparatus you just saw, except it's huge. It's kilometers long. And what they did establish was that, yes, in fact, gravitational waves do exist. They are emitted when large objects collide, masses change rapidly, and they ripple through the universe at near the speed of light. And they've been discovered and verified. They did that. Well, they did that on Earth. No, it traveled through the universe from a column. Basically, they watched two black holes combine.
Oh, they didn't do.
No, they waited, and they felt the gravitational rippling of space-time was felt on Earth from the merger of these two black holes using the same setup. Because the gravitational waves rippled space-time, the distance here and the distance, this mirror, and this distance shifted, producing changes in, they were using lasers, not just being, like, they were using, crazy lasers to do this. But there was measured changes in the laser that was recombined here. Let's add that. Okay, yeah.
Clearly show
There we
that
go.
the speed
I'll
of
keep going.
each light beam were different in different directions. But Michelson and Morley never detected such a difference. Their results were inconsistent with the existence of heat.
The scientific world didn't know what to make of it. Even the famous scientists in Europe, all Lord Rayleigh and Lord Kelvin and Lord Thomson, were saying, hey, come on, you must have done something wrong here. There has to be an effect. And the whole thing didn't get resolved until many, many years later when Einstein came.
Einstein's theory of special relativity proposed that the speed of light is always the same, regardless of the speed of the light source. The results of the Michelson-Morley experiment were entirely consistent with Einstein's view of the universe, and this served as the turning point in modern physics.
The Michelson-Morley experiment was an experimental advance in technology that transformed science. Not only physics, but science.
Because it didn't make sense. So he fixed it. Okay? Because there are, again, it's all about what are the implications of what we have just laid down. And the implications, therefore, to Einstein were that, okay, if light is a constant, what we know to be true about the space-time of our universe isn't consistent. So, consider these situations. We've got situation one. We've got a spaceship moving. A spaceship hovering at rest. Sorry, it's not moving. It's hovering at rest relative to Earth. Suppose the spaceship sends brief, regularly spaced flashes of light to the planet, seen in this picture here. Some amount of time will elapse before the flashes get to the planet, just as 8 minutes elapse before sunlight gets to the Earth. You guys know that? Light takes 8 minutes to get here, so the sun will explode, and then 8 minutes later we'll feel it. Okay. The light flashes will encounter the receiver. Sorry? The light flashes will encounter the receiver on the planet at speed c, since there is no relative motion between the sender and the receiver. Successive flashes will be received as frequently as they are sent. For example, if a flash is sent every 6 minutes, then after some initial delay, the receiver will receive a flash of light every 6 minutes. With no motion involved, there is nothing unusual about this. You're cool with this, yes? So in 60 minutes, the ship sends out how many flashes? And the Earth receives... Cool, flip the page. Situation two. We're going to involve motion. When motion is involved, the situation is quite different. It is important to note that the speed of the flashes will still be constant. This is the proposition from Einstein. No matter how the ship or receiver may move. How frequently the flashes are seen, however, very much depends on the relative motion involved. When the ship travels towards the receiver sees the flashes more frequently. This happens not only because time is altered due to motion, but mainly because each succeeding flash has less distance to travel as the ship gets closer to the receiver. If the spaceship emits a flash every 6 minutes, the flashes will be seen at intervals of less than 6 minutes. This makes sense, yes? Suppose the ship is traveling fast enough for the flashes to be seen twice as frequently. Then they're seen at intervals of 3 minutes. So the ship is sending flashes every 6 minutes, but traveling towards the Earth. He sees, our observer on the Earth, sees the flashes coming every 3 minutes. Because light is constant, it's the distance here that's shrinking. So in 60 minutes, the ship will emit 10 flashes of light. Each flash will arrive at the Earth 3 minutes apart. How long will it take the Earth to receive the 10 flashes emitted by the spaceship in 60 minutes? 30 minutes. So 60 minutes has passed on the spaceship, emitting those 10 flashes. But the Earth experiences all 10 flashes in 30 minutes, because they're coming 3 minutes apart. Sorry?
flashes start. So there's like a time lag between them still, right?
There was a lag in the first one too.
Yeah.
Like ignoring that lag.
That's
So it's weird.
so. What's weird about this? What's disagreeing with Franklin?
Well, if you're on the ship, it takes you an hour to send these flashes. If you're on the Earth, you experience the flashes in 30 minutes. What do you mean?
Wouldn't they not have happened?
You see that, but that's the point of your frame of reference.
Oh.
Because it's not, it's the amount of time taken, right? So that initial lag doesn't matter. If a guy on the ship says, I'm sending them every 6 minutes, so it's going to take an hour to send 10, regardless of that lag, the Earth still sees those 10 flashes coming in half the time.
Okay, but what if it was sound now, not light?
Well,
It
it wouldn't work that way.
doesn't.
It's light. It's light that's behaving that way.
The sound, or not sound, like the sound that travels with space, but like the physical object, they would see it every 6 minutes still.
Sorry, say that again?
So you throw a paper ball, like a really large paper ball, every 6 minutes, and you're still traveling towards Earth. The intervals are still going to be the same.
They should be,
Right. That's
right? That makes sense, yeah? They should be.
Earlier, the speed
Say that again?
if the speed of light is every 6 minutes,
Yeah.
then isn't the speed
No, speed of light has to be constant, so that must mean the universe is changing. Some aspect of the universe, either space or time, is not constant. In this case, what we're building towards is that time is not constant. Yeah. But see, that the radio is traveling at the speed of light. How do you coordinate? It's no different than a pulse of light.
So,
You couldn't coordinate.
after 30 minutes on Earth, they like have you done send the flashes, and then on the spaceship, they have already done send the flashes in 30 minutes on Earth, but it's been an hour on the spaceship.
No. That's not what's happening. Again, that initial lag doesn't matter. It's not like you're waiting for it to show up and then the next hour. Like, think about how this works. If I throw something at you every 6 minutes, you would be expecting to catch something every 6 minutes, ignoring the time it takes the first one to get to you. You would know then to look up 6 minutes from the first catch. In this situation, on the rocket, I am now pulsing light at you every 6 minutes, some distance away, as I travel towards you. It doesn't matter where you are, it matters how fast you're traveling. Flip the page. If the ship recedes from the receiver, i.e. is traveling away from the receiver at the same speed and still emits flashes of light at 6 minute intervals, these flashes will be seen half as regularly by the receiver, that is at 12-minute intervals. This is mainly because each succeeding flash has a longer distance to travel as the ship gets further away from the receiver. The effect of moving away is the opposite of moving closer to the receiver. So if the flashes are received twice as frequently when the spaceship is approaching, they are received half as frequently when it's receding. 6 minute flash intervals are seen every 12 minutes on Earth. The conclusion means that if two events are separated by 6 minutes according to the spaceship clock, they will be seen on Earth to be separated by 12 minutes when the spaceship travels away at high speeds, and by only 3 minutes when the ship is approaching at a very high speed. So there's a paradox here called the twin paradox. The paradox is this. Let's say you have two identical twins. One, an astronaut, twin A, who takes a high-speed round-trip journey in the galaxy, while the other twin, twin H, stays at home. When the traveling twin returns, he is younger than the stay-at-home twin. How much younger depends on the relative speeds involved. Depends on how fast and how far and how long. Could be years.
Like the movie
Like Interstellar.
How, like, would the difference, like, what would the difference be to create that much of a
We can do the calculations. We are going to do the calculations.
back? It's like every hour, it's like you're. Oh yeah.
So let's combine these things using the rocket ship and the light. So traveling away, you see flashes every 12 minutes, even though this guy's sending flashes every 6 minutes. On the way back, the ship is still emitting them every 6 minutes for a while, still receiving flashes at 12-minute intervals from a receding ship. For a while on the trip backwards, they see the 12-minute gaps, but then all of a sudden, the ship is these closer together shots of light. Even though he's still being sent every 6 minutes, the flashes are going to be seen as approaching from the approaching ship every 3 minutes. We cool with what's happening here? So let's apply this doubling and halving of flashing intervals to twins. Suppose the traveling twin, the astronaut, recedes from the earthbound twin at the same high speed for 1 hour, and then quickly turns around, that is the hard part, and returns in 1 hour. Follow this line of reasoning will help with figure 13, this figure here. The traveling twin takes a round trip of 2 hours, according to all the clocks on board the spaceship. However, this trip will not be seen to take 2 hours from the Earth's frame of reference. It will be seen as taking much longer. 4-hour trip. Here we go. Okay, so we're going to use our same reference time. Let's chart it. The ship is leaving the Earth. The time on the ship when the flash was sent. The flashes are going to be sent every 6 minutes. So let's fill this chart, and this is easy. 1, 2, 1, 2. 1, 2, 18. 1, 2, 24. 12, 30. 12, 36. 12, 42. 12, 48. 12, 54, and the 10th flash leaves the ship at 1300 hours, i.e. 1 o'clock. The time on Earth when the flash is seen, though, looks like this. As the rocket's traveling away, it's going to be 12 minutes. So this is going to be 12, 12. 12, 24. 12:36. You see now we're getting the separation in times here, yeah? 12:48. You asked for it. 1300. Bless you. 1312. 1324. 1336. 1348. And 1400 hours. Okay, then the ship turns around very quickly and it comes back. The time on the ship remains constant. It's every 6 minutes. 1306, 1312, 1318. The chart is just continuing from previously. 1324, 1330, 1336. 1342, 1348, 1354, and 1400. But on the way back, What does the Earth see? Every 3 minutes. So then from 14, we're going to get to 1403, 1406, 1409, 1412, 1415, 1418, 1421, 1424, 1427, and 1430. So the twin has traveled on the astronaut twin, aged how much in that time? Relative to itself. Well, no, from beginning to end. 2 hours. Twin saw itself aging 2 hours. The other twin, though, the twin that didn't move, traveled the normal amount, the normal amount of time on Earth. So now their ages are separated by half an hour. The astronaut is half hour younger than the twin. Sorry? Yeah, half hour younger. Yeah. There is an equation that relates all this together. And it says here, next class, it's not going to be next class, it's going to be in about 10 minutes. So, is it possible to travel through time? Yes. Also no, but yes. But also no. Special relativity that tells us that we can travel into the future, but not to the past. Quantum chronodynamics says that time travel into the past has to be possible. My professor said that to us once. We were finishing class. He's like, also time travel has to be possible. And then he walked out the door. And we're like, WTF. Why would you do that to us? But yes, there's some crazy stuff here. I'll show you. There's a couple videos down here at the bottom that are listed. I want to show you them as well.
Yeah, just go through about Don't worry.
Actually, you know what? No, I'm not going to do those. We're just going to keep going.
Thing is, though, you're not actually like, but that's the time that has made different than the other person. You're still experiencing your own time. Yeah, the time onto the person on Earth, not the time. Time doesn't change for you.
Time doesn't change. Well, time hasn't changed for either of the observers. In relation to each other, it has, yeah.
Yeah.
So when you take someone and move them really quick, really far away,
Their time goes like decades and like
okay, let me keep going here. Time dilation. You want a special relativity? Here we go. So we've already seen it. We have seen that time does not pass universally. Okay, moving at the speed of light or close or at some much higher speed. We've already seen that as far as these twins are concerned. They've experienced the passage of time at different rates. They each experienced time traveling for themselves at 1 second per second, which you would expect. But relative to each other, there was a difference. And there is a consistent way to calculate that difference. One of the effects of special relativity is this concept called time dilation. Dilating is something you normally associate with what part of your body? Your eyes. They grow or they shrink relative to the amount of light present. Lots of light, your pupils shrink. Not enough light, your pupils get really wide. They dilate. Time dilates, depending on the speed of the traveler. Albert Einstein comes along with the following explanation. He has two postulates. There are only two postulates to special relativity. Rules. The first postulate is this. If two frames of reference move with constant velocity relative to each other, so acceleration is 0, then the laws of physics will be the same in both frames of reference. Not what it says. So the laws of physics will remain the same in both frames of reference for two frames of reference moving with constant velocity, so no acceleration. In other words, if you pour a cup of coffee while on a jet that is traveling at 700 kilometers per hour, the coffee will still pour straight down. It doesn't pour backwards. If you poured it out the window of the plane, relative to you, what are you seeing the coffee do? Flow backwards. What it says is in both reference frames. So within you can't jump from reference frame to reference frame. You have to remain within the reference frame. So the stewardess, you and the coffee, or the steward, I guess, the person who's providing you the coffee on the plane, regardless of gender, can safely actually pour the coffee. Because you're all within the same reference frame, a non-accelerating reference frame. It's like playing catch inside a car. Also works. Okay? But if we were playing catch between cars, it could work. But if we're playing catch in an accelerating car, it becomes a little bit more challenging. As long as you aren't accelerating. So there's no difference between standing still and the throwing up and constant velocity, the throwing up. It looks exactly the same. What we could do, though, and we're going to do down here at the bottom, we're going to sketch what the path of the ball thrown in the van would look like to an observer standing on the road looking into the van as it passes. So this is where things get tricky, because what you have to do is you have to picture, okay, I'm standing on the side of the road. What is that? I'm standing on the side of the road. The van goes by. Person throws the ball up and comes back down to them. They see the ball doing this. What do you see the ball doing? And the hard thing is you have to picture what the ball is doing. The van's gone. The person throwing the ball is gone. We just have to picture the ball. The ball is zooming. So what's that shape going to take? It's going to look like that. Look like an arc. Because the ball has some relative to, like, you're outside the van. Outside the van, the ball has some horizontal component of velocity, i.e. the speed of the van. When you're in the van, you also have that horizontal component, so you're traveling with the ball, which is why you, in that frame of reference, you just see the ball go up and down. But the person outside the van says, no, the ball did this. The ball was a projectile undergoing uniform motion for a projectile. It's interesting. There's implications here. That first postulate, that's my line, right? The entire time we've been in person, what is the implication? There are implications. The second postulate of the relativity principle is this. The speed of light in space is the same for any observer, no matter what the velocity of the observer's frame of reference is, and no matter what the velocity of the source of light is. This is weird. The speed of light must remain constant. Is the boiled down version of that statement. The implication of that is this: your time and my time don't have to be the same time if we are in different reference frames. We're all experiencing the same time right now because we're all in the classroom together. All of us are not moving. But as soon as Zach gets up to go to the bathroom, the passage of time for him is going to change relative to us. We've already said this, but I'll write it down just for the sake of this. To dilate means to make wider or larger. Your pupils do this. According to Einstein's special theory of relativity, a clock that is moving will do what relative to the Earth? Using the chart that we filled out earlier. What happened to the clock on the ship relative to the Earth? It slows down. This stretching of time by a moving object is called time dilation. you got the dude on the ship. From this dude's frame of reference, the light takes time A, or sorry, time rather, to travel from mirror A and back to mirror B. Okay? This distance here can be calculated using the speed of light times the amount of time that it takes. Distance is c, the speed of light, times t0. Is it possible that in two different frames of reference, identical clocks might run differently and that time might pass differently? Yes. This is one of the predictions of Einstein's special theory of relativity. This figure right here illustrates an observer inside an imaginary custom-made glass-walled spaceship. Highly specific scenario. Made especially so that an outside observer can watch an experiment done by an inside observer. The inside observer is watching an event consisting of an oscillating light beam. We're not going to watch the video. We're going to continue with this experiment. Flip the page. The oscillating light beam acts like a clock. Right? Like, think of the beam of light going back and forth, like the tick, 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 tick of an old school clock. We all have a mental picture of the clock ticking back and forth. Imagine that pendulum is replaced by a beam of light going back and forth across some distance. Equivalent, yes? Okay. The beam goes from the source up to mirror A, back to B. The inside observer measures the time for the light to travel from A to B and finds that time to be t sub 0, or t naught. Since distance equals speed times time, the distance that the inside observer sees the light beam travel is d equals c times t naught. He sees the light goes up and down, but buddy guy over here sees not that, because he is in a different frame of reference relative to the spaceship. He sees the light doing this. Light goes from here up to mirror A, back to mirror B, because as time is passing, as the spaceship is moving, the light has to bounce from that mirror to that mirror. It has to be, what's happening in reality has to be consistent. The light's balancing from mirror to mirror. You're not going to miss the mirror in one reference frame. Okay, we doing okay? Some of us are not doing okay?
This is the same picture.
Yep, well, it's the next step. It's, this is what is happening if you're inside. You go, oh yes, I'm flying around, lights going up and down. Whoop-de-frickin' do. Dude outside is similar to the ball in the van. Comes up, comes back down. This illustrates when an observer in a different frame of reference would see the outside observer is not moving at speed v. He sees the spaceship going at speed v relative to himself. To an outside observer, the light beam in the spaceship takes time t, the time he measures, to travel a distance of ct, while the spaceship moves forward at distance vt. We can look at how these two frames of reference are related using a very simple mathematical tool called the Pythagorean theorem. Get rid of that for a sec. So stay on this page. I'm going to flip back for a second, showing us this thing here. Nope, that's not, I'm flipping backwards, not going forwards. Flipping back here. So what we're going to look at is this. This distance here is c times t0. Okay, we've seen that already. That is what this guy is observing. This guy sees this. Light traveling from here to here as the mirror travels from here to here. These are all distances. This distance the mirror has traveled is the velocity of the ship times the time he sees passing. And this distance is the speed at which the light is traveling times the amount of time it takes. We're cool with that? That's the triangle we're going to analyze here. So that's the one that we're going to draw on the next page. We've got this situation. We've got a triangle, looks like this. We've got c times t0, ct here, and vt here. Using the Pythagorean theorem, how must these three sides be related? It's not a trick question. Vt squared plus, ct0 squared has to equal ct squared. So we're going to do some steps here. First we're going to bring in the squared terms. It's going to be v squared t squared plus c squared t0 squared equals ct squared, or t squared. And we're going to isolate for this term here. So we're going to get c squared t0 squared is going to equal c squared t squared minus v squared t squared. And then we're going to divide everything by c squared. Every term, both sides. Here they're going to cancel, here and here. So we're going to get t0 squared equals t squared minus v squared t squared over c squared. And then the last thing we're going to do, well, second last thing we're going to do, is factor out t squared from both terms here. We're going to get an equation that looks like this. t0 squared is going to equal t squared, bracket, 1 minus v squared over c squared. Anyone have any issues with the math that I've just done? Don't flip the page. Stay on this page, because there's still space at the bottom. Unless you're drawing like an elephant, or writing like an elephant. The last step that makes sense is to do what? Sorry? We're going to square root this thing. So we're going to get t0 is going to equal to t square root 1 minus v squared over c squared. Which time frame, t0 or t, is most interesting to us? T, why, Grissa Hill? No, stop looking ahead. Think about what we've just done. Where did time t come from? No, time t was relative to who? To? And the system was the rocket ship. So the person outside the rocket ship is the person on Earth. Okay? So the person on Earth is watching the rocket. So we're going to isolate for the Earth's frame of reference. So we're going to divide both sides by the square root of 1 minus v squared over c squared. And now flip the page once you've written that down. We're going to get this time dilation equation that just jumps straight into this box. T, the time on Earth, is equal to t0 divided by square root of 1 minus v squared over c squared. Where t is equal to the time on Earth so this is like the rest observer. T0 is the time on the moving object. V is the speed of the moving object. And C is the speed of light. So, do you want to break now? Or do you want to do a couple examples and then take a break? Which one do you want? You don't get both. Hands up for, yeah, I could use 5 minutes right now. Hands up for, let's see a little bit more and then take a break. Okay, here we go, a little bit more. A spaceship, an application of this. A spaceship is traveling at 85% of the speed of light. That thing's trucking. Because we've already seen that electrons moving accelerated between voltage plates are only traveling a couple percent of the speed of light. Somehow we got a spaceship traveling 85% of the speed of light. If 1 year passes on the spaceship, how much time has passed on Earth? So we're going to use the time dilation equation. We want the time on Earth. We know that the time on the spaceship has been 1 year. And that the velocity of the spaceship is, when we say 85% of the speed of light, all of these problems are done at multiples of c. So we're going to say that v, you would not go and then say, okay, well, speed of light is 3 times 10 to the 8, and so we're going to do 3 times 10 to the 8 times 0.85, and that's going to be a number that we jam into this thing. Don't do that. What we're going to do is we're going to say, well, this is just 0.85c, which is how you would do the calculation for the speed anyway. 0.85 times c. You're going to see what happens when we shove it into the equation here. So the time dilation equation looks like this. T equals T0 over the square root of 1 minus v squared over c squared. Plugging in values, we're going to get 1 over the square root of 1 minus 0.85 c all squared divided by c squared, which is going to give us 1 over the square root of 1 minus 0.85 squared c squared over c squared. Those c squareds are going to cancel. So what is 1 over the square root of 1 minus 0.85 squared? What is that value? So the ship's been traveling, as far as the ship is concerned. On the ship, astronauts like, yeah, we've been gone a year. On Earth, they're like, nah, you've been gone for almost 2. Blake, you already mentioned a Hollywood movie that references this exact phenomenon. Interstellar. I have actually not made it all the way through Interstellar. It was just, the day I was watching it, it was just slow. It was just taking forever. And nothing I saw was overly mind-blowing to me because I've studied it all. Interstellar was really mind-blowing to people who've never seen it before. But as soon as he leaves, the punchline to anyone who studied physics is already present.
What about the ghost in the bookshelf? You never, oh, he didn't get to that part.
I do know of the ghost in the bookshelf. But it's the punchline. Okay, here we go. So imagine you are 30A. A is just the units for years. That A stands for annum. That is a number of years. And you have a 5-year-old daughter. You're living in a cornfield. That's just a side story. Sounds a lot like Interstellar. You leave on a space trip in the year 2000, and you travel at 0.99 c somehow, or 99% the speed of light. Somehow. For a time, as measured by you in the spaceship, of 6 years. In other words, from the space traveler's time of reference, T naught is 6 annum. How much time will have elapsed when you return? You're gone for 6 years. From the frame of reference of your young daughter, I'm going to put that in quotes, who is left behind on Earth. T is 42.5 years. Well, I talked slowly enough that she jammed it through the equation using the same setup we did before. Because we've got T on Earth is what we're looking for. T0, the time is measured by the astronaut, is 6 years. The velocity is 0.99 c. I'm going to write this a little bit differently. T equals T sub 0 over the square root. I'm going to write it like this. 1 minus V over C all squared. I'm just going to simplify this piece. So 6 divided by the square root of 1 minus 0.99 squared. Because the C's have canceled. Hannah already did the calculation. It's 42.5 years. Verify that. Double check that Hannah's right. Joseph has... Okay. So what this means is this. Having left the Earth in the year 2000, you will return in the year 2042. Your daughter's going to be how old? 47.5 years. But you see yourself as only having traveled. So your daughter, you are now, excuse me, you were 30. You've gone for 6 years.
Oh, wait, I'm misreading this.
Your daughter's 47.5 and you're 36. Interstellar. Spoilers, sorry. Yeah. Yeah, that's weird. Okay. So, it's theoretical and not theoretical at all.
But like it's theoretical because we couldn't travel that fast. One day.
Correct.
I thought it's,
But things do.
yeah, we need to believe. I mean, like you guys might not be able to, but it's like you can't tell.
Yeah, come on, Joe's magnets on the outside of it.
No.
So that
Isn't it no masses can't actually travel that fast? Again, just like you can't
all
let masses travel.
I'm pretty confident this is the one that I want.
I mean, I don't think anyone in NASA described being a Ferrari.
Yeah. Actually,
Okay. Pretty sure this is the one that I want.
To everything in our lives. That is why we're totally replacing it. Wait, what? In a couple days, the Air Force is launching another new GPS satellite into space. GPS 2F5 is the 5th upgraded satellite in a long-term plan to make GPS faster, more accurate, and more efficient, which is awesome, not just because I can't find anything more than a mile from my home without it, but also because it's used in everything from ATMs to dog collars to farming equipment. The first generation of the global positioning system was created by the Air Force in 1973 for doing complex things like finding lost soldiers and instantly figuring out the math required to launch a missile from a mobile platform. GPS, as you and I know it, started in 1989 with the launch of the first GPS-2 satellite. The new network was opened completely to the public in the year 2000. The GPS network is made up of 24 operational satellites and some extras for backup. 4 satellites always have a line of visibility to your receiver at any time of day. Your receiver gets information on the location of at least 3 of the satellites around you and the distance between you and those satellites. And using those measurements lets your receiver pinpoint where you are. It's called trilateration. Now, to do this, all the GPS satellites and receivers don't just have to know where they are, they have to know exactly what time it is when they're sending their positions. Say it's exactly noon and you check your GPS. If one of those satellites think that it's 12:01, it's going to mess up your position. It might think you're moving. That's why every satellite's got an atomic clock in it that is accurate to a billionth of a second. And every receiver uses a quartz clock that constantly resets itself to match its time to the last one it got from the satellites. And that's also why GPS isn't just used in positioning anymore. It's also used in timekeeping situations where everything needs to be synchronized perfectly. Stock market trades use the atomic clocks in the GPS network because just a fraction of a second could change the ownership of billions of dollars. It's also used in ATMs. With more and more of our lives becoming dependent on GPS, it's not surprising that a massive upgrade is underway. Type 2F satellites like the one being launched in a few days are considered interim upgrades that have a 12-year lifespan, improved clocks, and a new type of signal for everyday use. And by 2020, we'll be using Type 3 satellites. They're going to have newer clocks that are accurate to a fraction of a billionth of a second. Super important for military and financial uses. They will also have increased signal strength and accuracy. While GPS is accurate to about 20 feet, the new Type 3 network will be accurate to an arm's length. I don't know if that's like a tall guy's arm or my arm or like a baby arm or what, but I feel like my eyes might be able to take it from there regardless. If you're interested in the GPS network, ours...
Okay, so that is a crash course on the GPS system. But look at what we've just studied. Those things are in orbit. We can figure out their speeds in orbit depending on circular motion using forces, gravitational forces. The implication there is what? What's going to happen to those things in orbit as time on Earth travels?
They're going to last longer than 12 years.
Looking at special relativity, those clocks are going to alter, or going to be changed relative to our time here on Earth. Yes.
Does that mean that lifespan would be longer? Yeah.
Well, lifespan is weird because we are the ones that measure the lifespan of those satellites. So, as far as we're seeing on Earth, those satellites are aging. However, those satellites are aging. We dictate that time. The problem is they have atomic clocks on board. Those atomic clocks measuring time are traveling at a velocity that is high, well, a different velocity than we're traveling. So here's us stationary on Earth, and there are atomic clocks traveling through space. The passage of time on those satellites is going to be different than the passage of time here on Earth. There is an impact on those atomic clocks. That now is where we're going to take our break. Take 5 minutes. When you come back, we're going to look more into this. Yeah, go for it. Take 5. Sorry? Yeah. So they should be active this year. I have no idea. Yeah.
That's pretty awesome, actually.
When Blake gets back. I don't need the science. Not even.
My
Noel's just going. When he gets back, you can go. Which movie? Snakes. What movie I went to? She was working popcorn. She works with her. Oh no, it would not. Oh, tell her it would not have been weird. Because I expect to see students that I know working there, and I didn't, which quiet place too.
I calculated how much younger I would be if I drove on the highway for an hour. It's 7 years.
They're very small.
Yeah.
Yeah.
I'm very proud of myself for this.
You found what percentage the speed of light was of that 100 kilometers per hour?
Yeah.
Sweet.
Very small.
It is very small. But now change that. Instead of traveling on down the highway, put yourself in a plane. Travel at 700 kilometers per hour. So with that, see with that 700 kilometers per hour. That's roughly the speed of a 747.
Is there real?
No. No. Can't be. That's the Michelson-Morley. It was in the video. Medium that light was supposed to travel through. Right, yeah, it would be like a field that would permeate the universe. And they've established it doesn't exist. Sorry, one second. Sorry? Same length of time that you were driving. Sorry? Sorry, carry on, Joseph.
Everything in the universe travels at speed is relative to something else, right?
Yep.
So there's nothing in the universe is stationary.
Right.
My dad really loves it. Yeah, we watch it like every year. I watched that. Read up, what's your favorite movie?
My favorite movie? There are many.
Oh yeah, I forgot. You like it a lot.
There are lots of. There's a time and a place, sci-fi, fantasy. You know, your historical war,
Space Jam.
Space Jam. There's a time and a place for Space Jam. Space Jam's definitely in the top 100,
I really like it. Top 100.
but it is different. But it is different because that doesn't really. Who is that matter to you? You just found it for 1 hour. Imagine that that's your living. You're a flight attendant or a pilot. Yeah. Imagine making that flight several times a day. As a flight attendant or a pilot. Okay, so let's say your job is you are a WestJet pilot. You fly to and from Calgary. But they can do it 8 times a day. A single, well, let's say 6. Let's be conservative. There and back 6 times. So that's 12 travels. Every day, let's say 5 days a week for a year. Let's say it's 5 days a week for a year. Sorry? There's 52 weeks in a year. Just wait till you get married. I loved Up, and then I got married, and I watched Up. I was freaking nuts.
Up is really sad.
It's the first 10 minutes of the game. Okay, have you figured it out? Finish it, Anna. When Ashley gets back, we're keep moving.
Have you seen Luca?
I've not seen Luca yet.
It's like.
Didn't it just come out?
Yeah.
Like several days ago?
This weekend.
No, I've not yet seen Luca.
It's like, so you know how like the past couple of movies have been like really heavy emotionally.
Yeah.
This one's not like that. It's just kind of like a lighter story.
Okay.
It's kind of nice. It's like it's a good break.
Like Onward was pretty. That's not an insignificant amount of time. Yeah. That's not an insignificant amount of time.
And then like multiple years, we're not saying that, but they choose to make you pay.
But then there's other. You're not taking into account other problems. So, but Hannah, you're also not taking. Now you got to take. So that's the spectral relativity. But now you got to take into effect that as you go higher in the atmosphere, there's less atmosphere protecting you from radiation from space, ionizing radiation from space. A lead suit, yes.
So it's actually not safe to go on a plane? Like in that.
To travel on a plane, like a flight is fine. But you're as a pilot making your living over the course of your lifetime, there's a measurable effect on your.
So when we're talking about like the coffee.
Yeah.
So what if like the plane say like coffee? So the person outside the plane, when they see the coffee.
Yeah, I've already answered that question.
Yeah.
You already answered that question, Nathan.
But it would be going into the cup.
But the cup's also moving forward.
Are you saying
It's every picture that I put in here. Sorry? If she had a twin who wasn't a pilot, her twin is a high school teacher, she would get progressively younger relative to her high school teacher twin. That's the whole point of what I'm trying to teach you here. You would age at a different rate.
like they weren't gonna put that
It's all practical. You just like this application better than the other application. Everything I've taught you this year is intensely practical. You just don't like the application. Okay, Ashton's taking too long, so we're just going to start without him. Bringing it all back. Here we go. Oh, there's Ashton. Okay, so I found a piece of, I'm not going to show you the whole thing. I'm just going to show you a piece of it. GPS system, and it connects both special and general. We're not going to talk about general relativity, but it connects them both, showing you what the problem is here. So coming back, bringing this back here, show you a clip of the piece of this. Maybe not.
Apologies. This GPS system will not give you the right location. Here comes to solve. Even with
So, like as was said before, 24 satellites plus a couple backups just in case, orbiting the Earth in these patterns, so that at any given time, any location in Earth has access to 4 of these satellites. This is what it looks like.
all these advanced technologies, this GPS system will not give you the right location. Here comes the importance of Einstein's theory of relativity. Time is not absolute. It depends upon many other factors. According to the theory of special relativity, a fast-moving clock will slow down.
See, look, the time is different.
The atomic clocks, which are moving at a speed of 14,000 kilometers per hour,
Pretty quick.
will slow down by 7 microseconds every day due to this.
7 microseconds doesn't sound like a lot, but it's 7 microseconds per day. Yeah.
I'll like make my clocks, like my clock in my bedroom and my clock on my phone the same, and then like 5 months later I'll come in and be like, why is it in there?
No, your phone has other issues.
or into the phone.
This video actually deals with your phone's issues, but I'm not going to show you that part.
At an altitude of 20,000 kilometers above the Earth, the satellites experience 1/4 of the Earth's gravity. Thus, according to Einstein's general relativity theory, the clocks will tick slightly faster, in this case around 45 microseconds every day. This means
So the general relativistic effects make the clocks tick faster. The special relativistic effects make the clocks tick slower. So there's a net effect of
a
38.
net 38 microseconds of offset is created every day in the atomic clock. To compensate for this,
And they've, oh, I think it was earlier in this. You know what? I will go back. You know what? I won't go back.
a
Yeah.
theory of relativity equation is integrated into the computer chips and adjusts the rate of the atomic clocks. Without this application of the theory of relativity, the GPS would have produced an error of 10 kilometers every day.
That's a substantial amount. The number that's earlier in this video says that 1 nanosecond difference is equivalent to about a foot. So nano is 10 to the negative 9, micro is 10 to the negative 6. So that's 1,000 times different. So now you're talking about like 10 kilometers per day. That's not an insignificant amount. If I'm trying to find Subway and it tells me it's over there, but it's actually 10 kilometers away, I'm going to be hungry and angry.
GPS is a navigation system developed by the U.S. Department of Defense and is completely free for the public.
I mean, and you think about the applications when this thing was first invented. The Air Force. Air Force is big deal. Where can I put my missiles? If you're out by 10 kilometers. I don't think I need to tell you what the problem is with that. They have problems without being out 10 kilometers. And now add 10-kilometer difference on top of their targeting issues. We have lots of people who shouldn't be dying.
So there was this one day where I was late, just like extremely late to school because my phone automatically set its time zone to some other time zone. And would that be because of GPS or?
I have no idea.
Okay.
I don't know your phone's specific problems. I don't have an answer to. It might have been something to do with, but likely not. Well, GPS is likely not the problem. The phone is probably the problem. GPS is, as many things as rely on it, it's pretty accurate. It's important for them to fix it. Let's do a couple more examples here, and then I'll just give you some stuff to play with. Suppose a spaceship is trapped. Oh, Hannah, I think I want you to share what you calculated while we were on break time. So from the beginning of like the first problem that you tackled.
Since this was fun, I decided I was going to find out how much younger I would be if I were to drive on the highway at 100 kilometers per hour for 1 hour versus staying stationary.
Like instead of sitting in class, you drive to Vancouver.
And I found it to be 1.18 times 10 to the negative 4 years.
Younger. Did you converted that hour into years? Okay. Okay, so you found, but so long as you're consistent, that's the amount of years difference. Okay. Then I posed you a question. Because and I'll say why I asked the question. I posed a question because 1 hour to Vancouver, that's a relatively small amount, not a big deal. But what about people who do journeys like that all the time and at higher speeds? I was thinking like pilots and flight attendants. So that hour-long flights, I heard someone say, well, you're flying to Calgary. Yeah, it's just over an hour. Let's say you make that flight multiple times a day, 5 days a week for a year. That was the parameters I gave you, right? Go.
It was 700 kilometers per hour. I converted that into a fraction of
the speed of light.
And then I calculated how many hours total that would be per year, and divided that by the number of hours total in a year.
Okay. To find your years. Yeah.
And then I found that to be 0.36 of the year. Just over a third. It's about.
So 4 months.
From just 1 year flying.
That is a year of flying the same flight, Vancouver to Calgary, 8 times a day. No, six times a day, 5 days a week. Yeah, 6 round trips. Right, 6 round trips.
So you're saying we should all be pilots and live for like an extra being an astronaut.
Okay, so driving to Vancouver, the measurable effect is small, but you start to stack that up. And now imagine you're a pilot for a 20-year career. Like, it compounds.
Yeah, so we'd be living
Air Force pilot, your speeds are higher. Like, I don't know, all these, there's different factors to it that all definitely compound.
Oh, is that why flight starter looks so young and family?
No, moving on. Suppose a spaceship is traveling away from Earth. Ashton, you asked this question. 99.9% the speed of light, so 0.999 c. Back on Earth, 1,000 years have passed. How many years have passed in the spaceship? So, setting it up again, what do we know? What are those variables? So this is the equation that we're going to use. Again, t equals t0 over the square root of 1 minus v over c all squared. What do we know? So which variable is that? T. Okay, so t is 1,000 years. And we know that v is 0.999 c. What are we looking for? T0, the time on the spaceship. Okay? So we're going to have 1,000 equals T0 divided by the square root of 1 minus 0.999 squared. How much time has passed on the spaceship? 44.7 years.
What? You could be alive and like you've had several generations.
Several generations. That's putting it mildly.
I'm getting myself GTA 6.
Okay, another application. Here we go. Proxima Centauri is the closest star to Earth, also called Alpha Centauri. Sorry, the closest star to our solar system.
That's not.
It is 4.24 light years away. A light year is the measure of distance that light travels in 1 year. If you didn't know that. Suppose we build a spaceship. Somehow the spaceship has been built that can travel at 80% the speed of light. How long will the spaceship take to get there as measured by stationary observers on Earth? How long will it take to get there as measured by observers on the ship? What is the distance traveled according to the observers on the ship? Well, D equals V times T. Okay, so let's do it. The spaceship is traveling, V equals 0.8 C. We want how long it will take the spaceship to get there as measured by stationary observers on Earth. So we're looking for T. And what else do we know? Distance is what? 4.24 light years. So this is just going to become a D equals VT question. Light years we can write as 4.24 C years. Because it's 4.24 years times speed of light. That's the distance. So we can use D equals VT, but I don't want D, I want T. So we're going to use T equals D over V. D is 4.24 C divided by 0.8 C. How much time has passed on Earth? 5.3 years on Earth. 4.2, because the C's are going to cancel. Yep. How long does it take to get there as measured by observers on the spaceship? The first one was just using information we know. Constant velocity problem. Now they're on the spaceship. We got to use time dilation to convert the 5.3 years to their trip. We want T0. We know the time that we're observing on Earth is 5.3 years. And the velocity of the spaceship is 0.8 c. So T0 is equal to T times the square root of 1 minus V over CL squared. I just made that adjustment for us. So what is the time as measured by people on the ship? .18 years. Cool. Here's a mind-blowing question for you. What is the distance traveled according to the observers on the ship? According to the observers on the ship. Distance, Versailles. Don't just blurt out random stuff. G equals VT. The distance that they see, they're traveling. They see themselves traveling at 0.8 c. They see themselves traveling for 3.18 years. So, how far do they 2.54 c years. So, they see the distance as being 2.54 light years, when the Earth sees it as 4.24 light years. So they see themselves as traveling a shorter trip. That's weird. Yes, they see a different distance. Yes. Yes. That's the point. Yes. Yes, Nathan. Yes. Space as you understand it does not behave the way you understand it. Flip page. Here's another question. How much time passes if you're traveling at the speed of light? Well, it's the same thing.
Actually, yeah. What?
We've got how much time travels for you if you're traveling at the speed of light. So we're going to use this equation. You know what? Go to your formula sheet. We're going to toss these on here. T equals T0 over the square root of 1 minus, write it like this, V over C squared. Toss that down there. And then its neighboring equation, T0 equals T times the square root of 1 minus V over C all squared. Toss those on there. So we're going to figure out how much time passes for you as you travel the speed of light. So T0 equals T, the square root of 1 minus V over C all squared. But you're traveling at C. So you're going to get T0 is equal to T, square root of 1 minus C over C all squared. So it's going to be T0 is going to equal T times the square root of 1 minus 1. 1 minus 1, last I checked, was 0. Anything times 0 is... So how much time passes for you while you're traveling the speed of light? None. Time does not travel for you. Time does not pass for you while you travel at the speed of light. So particles of light don't age.
So you're saying if we thought that I go kind of like what the hell? You won't age.
So light doesn't decay. Sorry? See, the problem here is the coming back to Earth. Changing direction requires what? More importantly, changing direction requires a force, requires an acceleration. So acceleration means you're changing your velocity. As soon as you start to change your velocity in any way, now you're no longer necessarily just traveling at just C. That acceleration, all of a sudden, you're going to age rapidly. As you change you're going to start aging again. Let me turn around. You'll still be younger, but there will be a time in that turnaround where you age. The speeding up, you will age while you're speeding up. You will age at the turnaround, and you'll age coming back. So you'll still be younger, but there are still stations of that journey that will age you. That's the important thing to remember. But you're also not getting back to Earth necessarily. So even though for our stationary reference frame on Earth, we say that it can take light from stars thousands or millions of years to reach us, in actual fact, relative to the beam of light, how much time has passed? None. As far as the beam of light is concerned, it took no time to get here from that star. as far as the light's concerned, yeah. Not for us, but from the light.
But like, I remember in grade 10 or 11, they were teaching us how light from the sun. Like
Yeah, it takes 8 minutes to get here, relative to us,
but they're like,
but relative to the light. Excuse me. Excuse me. 3. How many do I got? That might be it. Okay. Here we go. A spaceship is traveling at 2.85 times 10 to the 8 meters per second. Leaves the Earth. And returns 100 years later relative to the Earth. Now we're not using a percentage of C. We're using a value. 2.85 times 10 to the 8 meters per second. How much time has passed for those living on the spaceship? The procedure is functionally the same. We want the living on the spaceship. We want to know their time. So which of these equations are we going to use? Yeah, we're going to use T naught equals because that's what we want on the ship. So we're going to use T0 is equal to T times the square root of 1 minus V over C all squared. Speed of light is at the top. It is not at the top. Let's add it to the top. We're going to toss it in there on the E and M section because the light is an electromagnetic wave. C is equal to 3 times 10 to the 8 meters per second. Toss that up there in the E and M section. You never know.
no, this is
T0, 100 years have passed on Earth. 1 minus 2.85 times 10 to the 8 divided by 3 times 10 to the 8 all squared. How much time has passed on the ship? Standard scientific units is seconds. But as far as the time relates here, it's a years by some constant. 31 years. 0.2 years. So far, we've really been abusing this whole conversion of time thing. We haven't found anything fun. Oh, we have found some things fun. That's not true. Let's just use it differently. Suppose the spaceship leaves the Earth traveling very fast. It returns 20 years of Earth time later. However, only 10 years have elapsed on the spaceship. How fast was it moving? Here we go. So, assuming nothing weird has happened, yes. So we've got T and we have T0. Which one's which? T is 20 years. T0 is 10 years. So basically, how fast must they be traveling to have the time? So we've got actually stop for a second because you're all plugging in values and then moving things around, right? I'm going to manipulate the equation first to show you something cool. We've got this. This is the equation that we're going to start with here. T equals T0 over, no, I lied. That's not the one to start with. I'll start with this one. T0 equals T times the square root of 1 minus V over C all squared. First thing we're going to do is what? Nope. We're going to divide by T. Cancels out there. Next thing I'm going to do, yeah, I'm trying to isolate for V. Next thing I'm going to do is square it, both sides. So cancel out that. So I've got this. T0 over T all squared equals 1 minus V over C all squared. I'm going to add this piece over and subtract this piece over. So we're going to get V over C all squared is equal to 1 minus T0 over T all squared I'm going to square root both sides and multiply by c, giving us v, our velocity that we're looking for, is equal to c times the square root of 1 minus t0 over t all squared. Well, doesn't that look familiar?
Wait a minute.
We had the time on the ship is equal to the time on the Earth times the square root of this term here. Now we've got the velocity on the ship is equal to the speed of light times this term here. There is beautiful symmetry. That's all I wanted you to see here. Beautiful symmetry in the special relativity equations. Yeah. Is basically what that means, yeah. Okay, so what is that speed v? Can you give it to me as a multiple of c? Just basically, what is this expression right here? What is this expression right here? 1 minus t0 over t all squared square rooted. Okay, so v equals 0.866 c. 86.6% the speed of light. Which you could convert into meters per second, but so much of the other stuff that we've done has been given to us as that percentage. We've used that percentage as well. Cool. You like it. We do. Yeah. I'm not going to do example 8 or 9. There's a note I want to address with you, though, down here. For now, we are assuming this. Acceleration is 0. Okay? Special relativity doesn't handle the accelerations well. Einstein at this point did not know how to work into acceleration into his equations. In fact, the theory of special relativity should really be called the theory of special case relativity. That special case is when acceleration equals 0. The entirety of the theory of relativity includes the special case plus the general case. Gets put together as the theory of general relativity, which we are not even going to begin to touch in this course. Special plus general. This came 10 years later. Is theory of relativity. When people talk about the theory of relativity, should you go on and study physics? When you study the theory of relativity, it's everything. It's the special case without the accelerations traveling near the speed of light, and then there's general, which brings in gravity and the acceleration component. Things get wild. It's awesome. So classical physics. Oh no, special relativity is verifiable. It's absolutely verifiable, and it's very useful. The GPS system requires it. Like, the beauty there is that velocity is constant. For objects in circular motion, even though there's an inward acceleration, it's perpendicular to, the magnitude of velocity is constant. And it's the magnitude that's what we care about here. So, I got through almost all of special relativity. There is one more. There's one more little chunk of special relativity that I'm going to do with you guys first thing tomorrow. Yeah, I at least want to show it to you. It's not very long. Yeah, it's so time dilates. I already showed you one. Lengths change when you move fast, because they saw, the observers on the spaceship saw the distance that they traveled had changed. It shrunk. So there's another effect called length dilation. And special relativity also does something to your mass.
Oh, yeah.
Makes you heavier. So distances shrink, masses increase, and time slows down when you're dealing with special relativity. As you approach the speed of light. Well, it's a measurable effect there too. But the mass and length one, see, time, the beauty of time is it's cumulative. It adds. Time always adds. Mass doesn't. It would be while you're traveling at that speed, you would be slightly heavier. When you slow down, you would become lighter again. Yes, it's actually at the speed of light, it's infinite. You have infinite mass at the speed of light.
So for 0 time, you will experience a force of.
Well, not even. You're experiencing infinite mass. For as time stops, and that's the problem with reaching the speed of light, because we talk about, oh yes, ships, this moves at the speed of light or that moves at the speed of light, but as you go faster and faster and faster, the mass that you have increases at a corresponding rate. So the force required to move you is going to increase, because force is equal to mass times acceleration. As mass increases, to maintain the acceleration, the force has to increase as well. So things get wild, and distances shrink, which means you experience at the speed of light, you would be infinitely thin, infinitely massive, and time would not pass for you. No. Couldn't do much. So I do want you to play with this stuff, practice it a little bit here. Flip the page. There are some questions for you. There are 21 questions. I'm not going to get you to do all 21 questions. There is an answer key to all of those 21 questions on the next page. And here's the ones I want you to do. No, it's not, but doing some of it is good. I want you to do one. One is good. I want you to do. I want you to do. I want you to do 8. Oh, no, 4. I want you to do 4 as well. So 1, I want you to do 4. I want you to do 8. I want you to do, because 7, 8, 9, 10 are all the same. I want you to do 12 and 14. I want you to do I do want you to do 15. You're going to do yeah, so that's 40. Oh. I want you to do 19. And I want you to do 20. Read 20 really carefully. Yes, it's a paragraph. There's an A, B, and a C section built up in there. So let's write that down. You're doing 1, you're doing 4, you're doing 8, 12, 14, 15, 19, and 20. Yeah, lots of time. And it's not a hard calculation. It's the same kind of stuff that we've done before. And I told you tomorrow is going to be mostly review. It is going to be mostly review, but I am going to start the day finishing special relativity because there is not much left. Whole thing.
It took Einstein how long to figure out all the special relativity?
And we
Yes, assuming.
we figured it out in 3 hours. Come on,
I bet you like 1 Sheldon should just figure it out like that.